So good morning, everyone, and welcome to my talk on the cybersecurity Goldilocks problem, finding just right algorithm to set smarter thresholds. Whew, that's a mouthful. But don't worry, we are going to talk a little bit more about each and everything that I talked about right now. So we are going to talk what the cybersecurity problem is, exactly why should we even care about it, how many times have you heard the problems of good decision making, and then I have two use cases over here. One is for the risk score and the other is for tiering. And the last thing, we have a few demos and a few Google Sheets to go over, but I'll have open questions for you if you have anything regarding the algorithms that I'm using or why did I even start thinking about this. So without any further ado, let's get started and just talk about who am I. So my name is Rachana Kamat. I work as a senior security engineer at Samsara. Before that, I have completed my Master's of Science in Cybersecurity from Northeastern University, Boston. I am also the board member of the training and development team for the Breaking Barrier Women in Cybersecurity, where we focus on leadership and training people in the field of cybersecurity. I have previously spoken at a few conferences before. One of them is the Grace Hopper Celebration, Women in Cybersecurity conferences in Denver, and the Day of Security, India. My areas of interest are zero trust, security architecture, and design, and also sec DevOps. So if you want to talk more about it, I'll be there. Fun fact about me, I forgot to add it in here, but I'm a big space fanatic, so you'll see a lot of things which is like space related. Just wanted to make this fun. Okay, so I want to get started with an informal poll over here. So how many of you, when it comes to like making security decisions in the past, have fallen in this trap of guesswork? You know, you think about that intuition that comes in when you think about this feels risky, let's just mark it, or like this feels important, let's just go ahead with it. Show of hands, please. Okay, so quite some people over here. So if you resonate over here, let me let you know that you're not alone. This is what I like to call the Goldilocks problems of security. So just like our planet Earth is right in the habitable zone, as I said, space. Not too hot, not too cool, just in the right spot for being habitable and flourishing life. That's what I think we as security professionals are always trying to do, finding the optimal decision-making point. So not like the planet Earth, we're not thinking about temperature definitely, but we're thinking about what security decisions can we make so that we can justify why that was the optimal point for making that decision. So moving away from trying to go away from that guesswork, averages, which leads us to like simplistic and subjective approaches, we're thinking about those points of like using algorithms or data. So if you haven't thought about it before, we will be going through that discussion today where we can see how we can use the power of data and algorithms to make security decisions more data-driven. So let's get started on it. One thing that you all must be thinking about is why should I even care about it? Like, why are we caring about the just right spot, right? So the answer is, I would say, two extremes. One is what I like to call as the simplistic rules, and the second is what I like to call the expert guesswork. So let's start with the first one, right? The simplistic rules, which is usually driven by like averages or like arbitrary thresholds, is one where you're thinking about, okay, this point or this number looks good. I see a lot of number in that range. Let's just go ahead with it. Whereas you also can think about like industry standards. Everything in the industry follows this particular standard point, or like vendor is suggesting this particular standard point. Let's go ahead with it. Now, the problem with this, if you think about it in the cosmic analogy, right? I talked about Earth being in the habitable zone, but if you think about averages and distance from the planet Sun, there's a possibility that even Saturn and Jupiter can be considered as habitable zones, which is not really true. Both of the planets are like gaseous giants and do not have any conditions for life. What happens with this kind of problem is missed nuances, where you have like your applications, which are most important, or you try to call them as crown jewels, are left open. There are a lot of vulnerabilities, you don't care, you don't know about them. And then there are those least important applications which get more importance than they really need. This results to, like, I would say, resource inefficiency, because you're trying to focus your resources on things which do not matter, or like things which really are important are not given that importance in life. The other part, as I talked about, is the guesswork, right? To think about in the cosmic analogy, there were like brilliant scientists in the past who used to create and discuss about planetary movements just to like bare naked eyes. That they never used telescopes, or they never even thought about like using advanced mathematics. What caused this was a flaw in the model that they created. So one example I have over here is where scientists used to think that Earth is in the middle of the entire solar system and everything else revolves around Earth. As we all know, that's not true, but that was considered to be like right because an expert talked about it. The problem with this is the arbitrary thresholds, where your decision making depends on who made a security decision at that particular time or that particular incident, and it's never driven by objective data. So that's why I say we need to figure out a way to find the security sweet spot. So before I can actually go and dive into all the algorithms and things that I have, I wanted to talk a little bit more about these algorithms or try to demystify this with you. Because I think everybody who's sitting over here has been using algorithms in their day-to-day life without even thinking much about it. So let's give you a simple example of like clothing, right? Clothing industry or the apparel industry have put a lot of money and investment into understanding what the body shape or sizes are. So what they're trying to do basically is trying to say medium. What they really mean is like they're trying to use distribution to understand what the average body size would look like. And as you move to the left, to the right, they're getting the different sizes from small to large to extra large. So what I'm trying to say over here is what they're trying to cater is trying to get the majority of their audience with the things that they need while making sure the other people with a different body shape still get options for it. So basically, when each and one of you are going for any shopping, what you're trying to do is categorizing yourself depending on the statistical distribution overall. The other things I would say, which is a little bit mundane, but we think about it, is the playlist. For example, if you use any kind of applications, you must have seen that you have groupings over there depending on your genre, mood, tempo, and other things. Or let's think about like doing laundry, right? Do you always throw all of your laundry together in a basket and do the drying and the washing? Hopefully not. You try to create an organization of like your whites, your colors, and then you think about your delicates, and then you go ahead and create this organization for better processing. So what you're trying to do is basically have a diverse set of items, trying to gather them in a way that they are similar in some fashion, depending on their nature, and then try to process it for better efficiency. That is what the K-means algorithm will be doing that we're talking about next. It's basically organizing things based on their natural characteristics. So what I'm trying to say is algorithms are not alien concepts or like mystical creatures. They are something that are a formalized way of doing things which we intuitively do on our own. You have been thinking about them a really long time. It's only the names and the way, the methodology that we think about them is just standardized using some formulas in there. So that's what you're going to do today, is use this data and algorithms and talk more about how to solve one of the biggest challenges that we have in security, and then go forward with a basic solution. So let's get started with, I would say, the very first use cases. Now, you must have seen this problem or this question happen to you as a security analyst, engineer, or even like a normal, I would say, a GRC specialist, that you would be asked this question: which of the applications that you have in your environment is like the most important crown jewel? What do you normally do? Do you usually think about, okay, GitHub, right? That sounds really important, code in there. Let's just add in there. Or do you think about like, hey, I have this vendor application which shows me a particular number like 700 and it looks good. Let's go ahead with it, right? So you're thinking about like arbitrary data points without actually thinking about your entire environment as a whole. So that's what the traditional methodology always does. The difference between your traditional methodology and something as we call the Gaussian distribution is basically two things. One is it shows you probability of an occurrence. So where in your traditional methodology you always think about find that threshold or that point, it's the other way around. Here your data would tell you what exactly is high versus you telling the data what exactly is high. It then helps you to understand what your entire data spread looks like, and then you can figure out, okay, this is my medium risk application, and anything which is beyond this on the right or the left are the ones which are either really critical or like low risk. So the benefit I would say of this one is, one, you can adapt to any of the risk profile changes. So tomorrow, if your business priority changes or your applications move from being like 200 to like 10,000 or more than that, you still have a standard way of understanding what that cutoff is. You don't have a static point, you have more of like your data to tell you where that point would come in the future. So that's what we say is the main differentiation. But let me help you understand more in an interactive way that I have there. So here I have like 10 applications which have risk score mentioned with them. So question to the audience over here, if I had to ask you, of this data that you see in there, which is the cutoff point you would think about a high risk application? Shout it out. 75, okay. Any other guess? 80? So is 80 included and 75 included or beyond that? Beyond. So 80 is not included. Okay, so let's go ahead with saying 95 is the only high-risk app, and the other one that we had is like 80 and 95. Okay, so we'll take that, and now let's go with the basic averages that we have. So we take what the range is, and I want to segment them into low, medium, and high. So we divide them into the segment size, which is 3, and this is what I get, right? So I get group 1 with 40 to 55, group 2 with 60 to 75, and group 3 is 80 to 95. I think, ma'am, you said the 80 to 95, so this is what the average behavior looks like. But I had a question for you. Does this sound good enough? There's a structure to it, right? I can see a low, medium, and high. But something is missing, right? As we're talking about like the data points. Like, it is not looking at my entire data. It is just looking at one threshold point and telling me exactly where it should go. But when we take Gaussian, there's a little bit difference in there. One thing, as you will see, is the average still remains the same. It's not moving. They're the same data. But there is something called a standard deviation. The easiest way to define that is the data spread. Like, it looks at all your data in your environment and then figures out exactly what the data spread is. It doesn't look at a point, but more of like how much distance is between there in each and every point. And that is the point that I would like to say is like that adapts to changes. So even after you have more application, more risk profile added in there, that standard deviation will help you understand exactly what should go. So if you look at it, and ma'am, you were right, the 95 came in the high risk application. But one thing I didn't ask you all is thinking about the low risk thing as well. So if you look at these things, the one thing you'll notice is there are a lot of applications which are coming in the medium risk space. There's one that came in the high risk. 80 surely was an outlier if you think about it, but was it really a cutoff point when you think about all the data? Did not come out to be that. And then finally, if you look at the low risk application, it just came in like 2 applications in there. So as I was talking about resource allocations, right? So if you're a risk specialist or you're a security engineer, and you have been asked to, you're tasked to basically say, safeguard your most critical application, now you just have to focus on the one application instead of thinking about 2 or 3 applications in there. And if your CISO or anybody asks you, why did you just select one application? You have a data-driven methodology tell you, like, of all the resources that I have in my company, I really want to focus on the one that I think is the most important application in our environment, and then go ahead and think about the medium risk application. So I will help you to understand that in a more graphical way or the visualized way. So this is what we try to call as the normal distribution or the bell curve because of the shape in there. So if you look at it carefully, you say it tapers off in the end, and in the middle, it just goes as a peak. If you think about this, this is a phenomena that we see around the nature, probably everywhere that we go, and also it applies to our security data, thankfully, is everything in the nature kind of is more of an average than being an outlier. So what I mean to say is an application can either be too kind of risky or has a lot of vulnerabilities, or can be perfect. It somewhere lies in between of saying I have an average risk for all applications. So this is what it looks like. The main important thing to think about Gaussian distribution is it doesn't take the a single point into consideration. It takes the all data that they have in their environment and then decides exactly where it should define your criticality. So as I was telling before, we were thinking about only low, medium, and high, but your Gaussian distribution also helps you to understand if you want to go beyond that. Like, do you want to define critical high and critical low as well? And there are different ways of doing it. And if you go into much depth, there comes different the standard deviation and averages as well. So what I'm trying to say is, in this application, you can see that I have about mu plus the standard deviation on the left and the right as my medium. But there are ways in your organization, if you think, no, I don't want that half spread, I want more of like a smaller spread and decide what the outliers are more, you can change that into two standard deviation and 2 standard deviation on the left, and you get more information through it. So you can divide your segments into a better, more segmented way. And what else do I want to talk about this? Let's say that you say, I want to add more applications, and let's say they have risk score, which is more than 75 to 90 range. So help me understand when you say, what do you mean by adapt to changes or adapt to your risk profile? This is what I have for you. So the blue one is the one that we had previously, but as we add more data on the right side, because the 75 to 90 was on the right side, you can visibly see the change in the mean, right? You can see that your mean basically moved a few strengths. Now you would talk about like, that moved, but what about the standard deviation? Now that depends on your actual application risk score, because it takes the risk score into account, as I was talking here. From this graph, you can't actually say if the standard deviation moved, but at least you know that the mean moved, which means it's adapting to the change that's happening. It's not staying at the 85 or the 70 or the 80 that we talked about. It's actually moving as it requires. This theory is good, but let's say you want to actually see if this works for your environment or not. Let's do a POC. How do you do that? So I have a Google Sheet example for you over here. So this is the risk scores that I have. I have a lot of criteria based on which I actually defined what a risk score is. I can talk about this after the talk, but what we'll be trying to focus on is the last column, is the risk score that I have over here. So about like 20 applications for this particular POC, and I have the final risk score. And what I try to do is use the magic of Gaussian calculation. So as we were talking about, I calculated the mean, which can be done with the average function. Then you're trying to find out the standard deviation or your data spread, which can be done with the std_def or the standard deviation function, and you get that. And as I was talking about, like, how do you define? So for my use case, I just wanted to define into a low, medium, and high. So I used the mean plus standard deviation and mean minus standard deviation as my definition for medium. So I get that range. So if you look at my calculation, it's basically just trying to figure out where that particular data is. And then anything which is below this would be low, anything above that would be high. And the last thing that I did was this. Is basically, in order to define what my low risk is, I said, if it falls in the range that I defined as medium, that would be medium. If it falls in the low one, it would be low. And the high one would be high. So if you look at the data carefully, the 90 and the 96, which is row 14 and 2, came out to be low, which, if you think about it, looks right, because that's like kind of an outlier. And then for the high risk application, I have like 3 of the total 20 applications that I have in there. So if I had to focus my resources, I would say I'll focus on the ones which are red or the high risk application, and then fall back on the medium one. But just to go one step ahead, which is not related to Gaussian in general, but as an operational security engineer, is I have the high ones, which are the ones that I need to focus on first. So what I did was saying risk percentile, which is nothing but telling, okay, which is the highest risk application that I can see. So if you see in this one on the row 8, that's the highest risk application that I have in there. And then compare it to that, how close are the other applications in format of risk profile. So if you see anything which is like 0.8 or 0.9, that's like the next closest application you need to focus on. So once you're done with the high ones, and when you need to prioritize the medium ones, you can use something as a risk percentile, and then also define. So not just defining why this is high, you can go a step ahead and be like, why am I focused on this first? rather than the other ones, because now you have a risk percentile of saying, okay, this is the riskiest one. I need to focus on that first. Coming back to this one and summarizing. So this is how we decided to calculate our low, medium, and high, and this is the final output that we have there. So next time when you're deciding to figure out what your risk profile looks like, I think you can start using the Google Sheet one to figuring out, does that even make sense for your applications? I have the app 1, app 2, and the risk score as a logic that I have used. You can use whatever your organization would think would be right. But again, this is good as long as you think about it from a POC angle. But as you scale or you want to do this as a continuous process, how do you actually go about it, right? So this is what the workflow that I have designed for us. One thing I would say is the example doesn't have the brain logic of risk score, but I'll help you understand exactly the input and the output stuff in there. So the first thing, if you want to automate, is you need to get more application inputs. So it can be any of the application input. It can be Jira. If there's any other way of getting like a Slack information in there, any webhook can get you the information, go ahead with it. For my purpose, I started using Jira. So for example, somebody said, hey, can you calculate what the risk score for GitHub is so that we can figure out if it is a high risk application or not. The next step is to figure out how do you actually trigger your GitHub actions, right? You can use webhooks, you can use pattern matching of saying like, okay, if there's a new ticket created, then go ahead and trigger the webhook. There are many ways to do it. For me, what I did was using Jenkins workflow, or you can use Tines, you can use Build Guide, whichever works for you. So every time a new ticket was created, I had a label on it, and that created that webhook of saying, okay, trigger this process because I need to figure out what the risk is. The other thing you can also do is doing a cron job where you have a lot of different application input in there, and every day it will basically trigger that application workflow. What I use next for orchestration is the GitHub Actions because I wanted to run a Python notebook as a brain behind it. So what I did was basically create a GitHub Actions, given the input, the GitHub application itself, and you can also parse your median and the standard deviation in there. I have a Python notebook that I've created just for this purpose, for showing you. This is not my actual brain logic, but I just wanted to show you exactly what I did. So one thing is when you think about your Google Sheet is like, there's a standard, or I would say a fixed mean and a fixed standard deviation that we created. But as I was talking about, like when you have more applications come in, that changes, right? So it becomes really tedious to actually go ahead, recalculate all the applications and actually determining which one is low, medium, high. So what I did was kind of create like a simulated risk score. So what it did is took all the combination of what are the different risk scores that's possible for your particular environment. So as you can see over here, I said, okay, calculate the risk score depending on the weight that I've given you. That's a 10 to 1 weightage one. And also all the possible values. So 1 to 5, 1 to 4, whatever it is. It takes all that and starts plotting that bell curve for me. So the importance that I would say, the advantage of this one is the next time when an application comes in and the score is, you don't have to recalculate everything. It already knows what your environment looks like and tries to fit in where exactly that point or the optimal point is. So if I run this particular thing, and let me just give you an example of like application risk score is 195. So it tells me, okay, you have 195 score, that's a risk percentile of 85%. Your mean was 165 and your standard deviation is 27. So according to that, I think it's a high risk application. Now let's do it again and say, I need something for 120. What do you think about it? So if you look at the last line, it says, okay, the risk level is low risk right now because of the calculation that we did. And if you look at the percentile rank, it's the 5 percentile one. And let's take something which is probably in the medium range, is 160, and it calculates again and tells you where exactly that point is. So this is the brain logic that you can use to determine where in your entire organization's bit of risk that particular application can fill in, and then finalize one last step, which is once you calculate everything and you have this thing, and you have the final output of saying, okay, this is a high risk application, this is a low risk application, The final or the closing step, I would say, is go ahead and add that in your Jira input so that you have an auditability of saying like, okay, this was calculated, this is what the artifact looks like, and finally, this is your high-risk application. And now you have an entire end-to-end pipeline of actually getting an input, running that through your pipeline for Python, and then figuring out what the final step is. So this is a good way of, I think I would say, using CI/CD pipeline to having a live or a cron job to actually determine everything. And that is what we come to an end for the first use case. I hope everybody is comfortable with the way the algorithms are being defined. The next one that I have for you is basically the k-means algorithms. The second, I would say, use case is where you think about clustering. So you have a lot of applications in the environment. Not everything is important to your customer, not everything is important to your business, or not everything is important to your internal services. There are different clusters or like groupings that you think about, or you would say tiering for your application. That is important to understand which applications are critical for which department in general. So when you do a manual or a traditional methodology, there's always that manual point of saying, okay, anything which falls under 100 would be tier 1, below that would be tier 2, anything beyond that is tier 3. The problem with that approach is, one, it is a static approach, which means when your risk profile changes, your business priority changes, more applications are introduced, you'll have to recalculate everything. Was that 140 a good point, or I need to go beyond that? You'll have to go back and define all the other applications in general, which is not feasible, right? It's not standard, doesn't make sense. It doesn't scale poorly. Like when you get more resources, when you get more applications in there, do you really go ahead and define everything, or there should be a way that it adapts to it properly? So this causes inefficiency in your resource allocations as well. And since there's so many arbitrary values, there can be human debates by saying like, is this the right point? What if I define a different point in general? Or I like to call it as like one size fits all. So the approach that k-means follows in a different way is using algorithms, or like the algorithmic way of using standard information, so that you can have to move from this static way to more of a dynamic way, so that when a new risk profile is introduced or a new application is introduced, it can naturally adapt to the clustering in there. You don't have to think about the scalability in general, because now you have an algorithmic way of thinking the same thing. You can focus on more the insights or the final results than actually thinking, what should I do with this data, or where the tiering should go. And that actually helps you to make it objective and repeatable, because now you don't have to think about like, oh, 10 new applications are there in the environment, what should I do next? So let's start with the basic thing that we always do is, I have an example for you. So the app A and the numbers in there. So left side is basically customer criticality, and the right side is business impact, which basically means the left side is how much important it is there for your business and your customers, and right is more of like how important it is there for your business or your internal revenues in there. So if I had to ask you this question and I say, can you help me tier them up? What is the methodology that comes to your mind? Like how would you first go about thinking tiering these applications up or grouping this application?
I would sort it by first business impact, the customer impact, then second sort business impact.
Got it. And then you would basically see like which comes first and yeah.
Four groups.
Okay, that's a good. So what you're trying to do is kind of making a judgment basis on each dimension, and then figuring out what comes first and bubble them out. Okay, good approach. Any other things?
Kind of like just four groups: high, low, high, low, high.
Okay. So can you help me understand more on like when you say high, do you mean the?
If the two numbers are high, it's like business critical and everything. It's like
Okay.
If they're both low numbers, they'd be in low group, and then if the first number's high, the second one's low, then you kind of decide which is tier 2, tier 3.
Okay, got it. So I think both are good approaches. What I asked one of my colleagues when I was joining this, she said that you can actually try to do a summation of it and see if the number is greater than 140, it can be tier 1. If it's between 100 to 139, it can be tier 2. 50 to 99, tier 3, and anything beyond that is tier 4. So this is what I did and I got at it. But then one thing that came to my mind is, if I look at the application I and application J, right, and look at over there on the left side, one is higher on the business impact side and the other is higher on the customer impact side. The question that I had for me is like, why are they both in the same group? Because it doesn't make sense to me. And the second thing I said was, why are they tier 2? Like there are, if you compare the other applications like the C and G, if you look at it, they have kind of the same ratings for both. So why are they in the same group? So I wanted to go through with some kind of algorithms first. So I decided, okay, let's get started with some kind of grouping algorithm. And the first thing that came to my mind from my high school was k-means algorithm. Easiest way to do it. There are a lot more complicated things, but I wanted to do a POC. And when I did that, one thing I noticed was it moved. The application I and J, they're still on the same tier 3 group. I still wanted to understand why. But they actually moved from being a tier 2 application to tier 3, which kind of made me satisfied because, yeah, C and G doesn't appear to be the same natural grouping for it. The reason why this thing happens is the k-mean algorithm looks at both dimensions together and try to see a natural, I would say, bonding between those scores. It doesn't look at the customer value separately than the business impact because it's one application. So you need to understand them as a together value instead of having them separately. So that basically helps k-means to determine, okay, this particular resource kind of appears to be a high impact resource versus the other one might not be as impactful as the other. So let's go back to the Google Sheet one to get started with. So I have these scores, right? So what we try to do is kind of reach out to our customers and our business and say, okay, give me votes from 1 to 5 and try to determine how important that is for your business. And then we calculated what the total votes were. The first thing that I was talking about in my mind was like, I cannot just say that application 1, for example, has like 25 votes. So it's like the most important one. But as you can see, the total votes were 27 as compared to like application 15 in row 17 as 8. So how can you say that both the application? What if an application owner did not fill it out? There are like human biases, human prone errors that can happen. So what I did was like I created a weighted score calculation first. So basically take the weights of the total votes that I have in there so that I can look at all the score in a standard format instead of having biases of one score being higher than the other because some people filled out the form, others did not. And once I did that for both the criticality score and the normalized score for the business impact and the customer criticality. And the last thing that I would like you to focus on the other was the weighted final criticality score. I did do a sum, but for me, my business customer impact should be more than my business impact because that was the definition that I was given. I was told we need to focus on the applications which are more important to the customers because that drives revenue as compared to the one which is not as customer facing and not as business impactful. So I gave a 3 rating for the score for the customer impact and 2 for it. And then finally created that overall criticality score. Now, once I got the score, the next question that I had for me was, okay, how do I actually start grouping them now that I have the score? The first thing that the k-means algorithm teaches us is using centroids, or the easiest way of telling them is basically centers for clusters. So if I had to say, if you are playing with people and I ask you to create groups, you try to figure out which is like the center point for a group and try to come as close to that group as possible so that you look like a group. And that's exactly what the centroids with k-means does. So you can do the centroids in 2 ways. One is you can define the first centroid group or a first center group, or you can say k-means you just handle on its own, I don't care. But for me, so that because I was doing the POC, I was like, I know Datadog is important as compared to Slides AI or some other application. GitHub is important as compared to anything productivity like Spotify or something in there. So if I go back to my formulas, I just used like applications which are important to business, took one centroid for it, closest to it, And then I defined what my centroid should look like, because now once K-means starts working on it, I can be like, okay, Datadog, GitHub, all coming together makes sense. Whereas everything else, which is in a different cluster, should make sense on its own. So I use a centroid and basically try to calculate the distance from it. So think about center of a circle, and there are different points around it. You're trying to see what the distance from that particular center for different things are. So you calculate that for one center, you do it for the second, third, fourth, and then you try to determine, okay, which is the closest or the lowest distance from the centroid in there. So as you can see, I have all the centroids defined. Then I calculate the distance from the centroid, which is nothing but the square root of the distances. And then what I do for tiering is basically see which is the lowest one. So 13.18 is probably the lowest among the 4 that I see over here. And then if you go below a little bit, you can also see, okay, 2 is lower. Let's go a little bit more for applications. So for this one, if you say 1.3, 0.46, that's the lowest. So I mark that as tier 2. So you say that's done, right? But that's actually not really done, because K-means doesn't stop at just one iteration. What it tries to do is it tries to calculate the same distance again and again till the time the centroid doesn't move much. Like, for example, if I say if it's 12.1 and the next one I get 12.10, it's like, okay, it's getting stable. Let me look at the third iteration, 12.101, something etc. So like it's getting stable. So it makes sense I can stop over here. So it does a lot of iteration in that angle. So for my purpose, I was like, let me just do one more of this iteration and see what it goes. And I did the same thing. I created the new centroid, which takes the tiering into effect and takes the average of those tiers to figure out what the center point is. And then you again define the distances. So this is what you finally get it, and this is what I defined the final tiering. So if you think about it, I did 2 iterations, didn't go beyond it, and still got like a good final proof tiering in sense of like 1, 2, and 3. So if you come back to my slideshow, this is what my summary kind of looks like. Is basically I had few applications defined as application 1 to 7, 1 to 5, 7, which came up as like tier 1, the highest tier possible. And then as I went ahead with the data that I have in there, I got to plot the others. But if you think about it, it quietly became a nightmare for me, because I had to do these calculations a lot. And I stopped at 2, as I was saying. Like K-mean doesn't stop at 2, it does a lot more iterations. And the main reason for it doing that is because for us as humans, we would think 12.15 and 12.17 close enough, but not really. There is like much more points beyond it. So I wanted a programmatic way so that this iteration nightmare and the time-consuming thing would reduce it a little bit. And I'm a security engineer. I can't use Google Sheet all day long. I needed a better way of doing it. So I used Jupyter Notebook again. And this is what I have. So you can use different arguments to make it more suitable for your environment. But what I did is basically use the criticality score and created a data frame, which is basically the data amalgamation of the application name and the criticality score. And then to not dive deep in the statistical one, but one thing I wanted to talk to you about is this. So the N clusters is basically how much groups do you want. You can define it on your own, or you can leave it to K-means to determine how many groups you can actually make. But for my purpose, I wanted this 4 tier, so I said I need 4 clusters. And this is the most important one, the K-means N clusters, because it tells you exactly how many clusters do you want. The random state is like a seed, like where should you start thinking about the centroids. Remember in my example, I used particular centroids. This is basically telling K-means use what you think, a random centroid. And lastly, the initialization auto is basically telling you how many times you want to iterate. So I can tell you iterate 2 times or 3 times, or you can just tell K-means do it how much ever time if you need, just let me know when it is, right? So finally, when I did that and I say, okay, use these clusters, and we can go ahead to tiering it, this is what the final result looks like. This is the same data what I actually use. So if you remember, there were a lot more ones as compared to twos, because I stopped being a human. I cannot do much of this calculation. But here you can see there are a lot less ones, which means you can focus on those risk applications a little bit better. And then you can have their tier 2 and tier 3 applications to do that further. So this is what the final k-means output kind of came for me. And we were able to group those applications in a much better format using the data. And that's the final output that I got. So if you look at the red, green lines, these are basically the centroids that we used. And the colors are basically the grouping. So if you look at it visually, it makes sense, right? So the red line kind of makes sense for that group. The green line makes sense for this group, and so on. So this is how the final output kind of looks like. And that kind of comes to my wrap. But before I leave with a few key takeaways, I would like to say we always try to find out what the just right sweet spot is. But I think we always fall back on the habit of like guesswork because it's too time consuming or like too much to handle. But today we saw how Gaussian distribution and k-means actually helps you to move ahead from those guesswork and move ahead from those one size fits all. There are a lot more algorithms that I did not talk about. There are a lot of more things you can optimize. So if you're a data scientist, data analyst, I think you could find much better algorithms than I did. So I think it's also a good collaboration opportunity for data science and cybersecurity to work together to define this. So as I leave you all behind, I would say go back to your security data, look at it into a different lens. I think your journey to just right algorithm just began. I hope everything was really valuable, and thank you for giving me this opportunity to talk to you today. I can talk more about any of the things you wanted to ask me about, but that's most of it from my end. So thank you, and I'm open to any questions that you have.